Moving on with formal charge. Now, formal charge helps us to figure out also the stability of different Lewis structures as we draw this process out. So it's very, very important to actually be able to determine how to figure out formal charge of a compound. So formal charge also helps us out, like with our carbon dioxide. We saw that before, that we saw, well, we can have two doubles, we can have a single and a triple, and it helps us figure out which one's actually more stable. So formal charge determines how we do formal charge. We take, first of all, the total valence electrons you have to work with, and with the dual Lewis structure, you will actually you need a Lewis structure to be able to draw the formal charge or calculate the formal charge first of all, but you're going to look at each of the individual elements within the structure individually. So first of all, you figure out the valence electrons of each element. You get that from the periodic table. Then using your Lewis structure, you'll subtract one for every bond and then one for every dot. And this, again, formal charges, like I mentioned, helps decide alternative Lewis structures. What the rule is, the smaller the formal charge, the more stable it is. And what I mean by that is actually the closer to zero you are. As you move away from zero, whether in a positive direction or a negative direction, you become less stable. So also important to understand is if you're checking out, if you're wanting to make sure you drew the structure correctly, your formal charge for all compounds that are neutral should add up to zero. If your compound has a charge, whether it's a positive or a negative, the formal charge should add up to the charge of the compound as well. So let's go ahead and walk through some examples. Let's deal with carbon dioxide first of all. In carbon dioxide, we realized back when we dealt with the situation, we had a deficit of 4. And so in our situation here, we make 2 singles into 2 doubles, or a single into a triple. And so we had these 2 structures. But we want to figure out, well, which one of these is actually more stable. So we actually will figure out the formal charges of each of the elements within the compound. In this situation, we'll start with oxygen. And since both my oxygens are the same, if I figure out one, I have the other as well. So oxygen I know is in group 16, so it has 6 valence electrons. Now, how many bars around one oxygen? I'll deal with the oxygen on the far left. There are 2 bars, so I subtract 2 from my 2 bars, and I subtract 4 dots, and it gives me 6. So I realize that oxygen has a formal charge of 0, which makes sense because back on the original table we've gone through, realized that oxygen groups, or anything in group 16, likes 2 bonds and 2 lone pairs. And so carbon in the middle, we know carbon's happy. It has 4 bonds. It has 4 valence electrons minus 4 bars. It's 0. And then we already did oxygens. The one on the right is the same as the one on the left, so it also equals 0. Now there's no charge on my compound, carbon dioxide, therefore the net charge is 0. We know we did things correctly. But then we draw out the second one and we realize, okay, we run this one out with our first oxygen on the left-hand side minus 3 bars minus 2 dots. My first oxygen on the left is a positive 1 formal charge. My carbon in the middle has a single and a triple, so I know it has 4 bonds. Its carbon's happy no matter what. But my oxygen on the right, now I subtract 1 from my bar and 6 dots, ends up being a negative 1. Well, the net charge, positive 1 plus negative 1, is equals 0. So the form is actually correct, but to figure out it's more stable, I look back at the formal charges of individual elements, and I realize my second one and my oxygens are moving away from 0. One's positive, one's negative. Therefore, as you move away, the further away you go from 0, the less stable you are. Therefore, my carbon dioxide, more stable form, is with 2 double bonds. Ammonium. If you remember back with ammonium was NH4, and so remember with the other key thing about this, when you draw out Lewis structures, when you have a charge on the actual compound, you must put brackets around it in the charge of the compound on the outside. So this polyatomic ion, ammonium NH4 plus, so we draw this out. So in this situation, we see like nitrogen is in group 15, has 5 valence electrons minus 4 bars, and my nitrogen has a plus 1 formal charge. My hydrogens all are 1. Since all 4 of them are the same, I'll do 1 multiplied by 4 to figure it out. So I have 1 valence electron minus 1 bar equals 0, but there's 4 of them, so I'll multiply by 4. 4 times 0 is still 0. Has a net charge of plus 1, which makes sense because ammonium is a plus 1. Now cyanate. Now cyanate ion, again, this one is, as we look at cyanate, cyanate OCN minus with this, we realize cyanate, just like the carbon dioxide, we end up having a deficit of 4. We could have a single and a triple or 2 doubles. And so both of them actually work out correctly, and they use up our electrons. So which one's more stable? Well, if we look at the oxygens, first of all, both of them, my oxygen on my one on the left ends up being a -1. My carbon's happy, has 4 valence electrons, it's happy, and my nitrogen is also happy, has 3 bonds and 2 lone pairs. And so that's exactly what nitrogen wants. So nitrogen is happy on my left-hand side. The net charge ends up being -1, which is correct because cyanate is a -1. My second one over there, I see my oxygen's happy this time, but now my nitrogen is not happy. So my nitrogen is now the one moving away from 0. And so the nitrogen has a formal charge of -1. Now the question is, both of them end up being exactly the same. So really the question is, who's more stable with a -1 formal charge? Is it oxygen or nitrogen? Well, this goes back to our last unit, and if you remember our octet rule, a full octet, but a half full octet is a half full orbital, is also stable. So in this situation, you realize that nitrogen is at a 3, P3, so it's at a half full stability point. But when it gets a negative, that means it becomes a P4, it moves towards an unstable point. However, oxygen in this situation will actually make a move towards more of a full orbital in this situation, so oxygen actually does better off, actually is moving towards stability, where nitrogen with the -1 formal charge is moving away from stability. So in the first one, we would say, oh, then my first one is actually more stable. Cyanate is with a single and a triple, because oxygen would do better as a -1 than will nitrogen. Resonant forms. Resonant forms, we already talked about this with resonant forms. In resonant forms, when we have 2 or more equally valid structures of the same compound. And so we just have to, with resonant forms, you have to draw out both of the 2-dimensional structures. And so I have an ozone, I had a deficit of 2. And so to make one single into a double, I had 2 single bonds to work with. I had to show the double bond on both single bonds. The truth is this, is that both of the bonds are actually hybrid bonds. Both of them are neither a double nor a single, they're a hybrid. And so in this situation, they are 2 equally bonds. But we don't draw it out this way. We have to draw out the resonance structures, and we show the double bonds and the double bond in either one of the single on either side in this situation. So to understand resonance structures. Benzene is another example of a resonance structure. You get into organic chem. Benzene, we have this 6-carbon ring. In this situation, very stable, but we have again 3 double bonds, where again my double bonds could be alternate where they fall. The truth is this: all of them are actually hybrid bonds. So another way to write out the benzene ring is just draw out the benzene and then put a circle in the middle, representing that again in this process all bonds are the same length. They're all actually hybrid bonds, a mixture between the double and the single.